Welcome to Maths with Bob. Today we're looking at applications of calculus to the physical world. This is the second in the growth and decay series. Okay, now today we'll actually have a look at something like Newton's law of cooling, where the rate of change of the quantity with respect to time is actually proportional to not only the quantity, but it's actually the difference in some sort of constant called r. This one here is actually a constant. A lot of times it's the room temperature, but it doesn't have to be. Okay, so how do we solve something like this? Well, the first thing obviously we do is we actually go dq dt. We sort of use this constant of proportionality to eliminate the proportional symbol. Q minus r. Okay, and we try and solve this. Okay, so the first thing is we're going to try and solve this. We'll actually go through the actual solution to this to start with. Okay, well, let's actually have a quick look at how we solve this. Well, we solve all these sort of differential equations just by usually just turning them upside down. Find the reciprocals if you like. And then we non-integrate with respect to q, so it will become integral of dt dq with respect to q equals, the integral 1 on k q minus r with respect to q. I'll just write dq. Now, the first thing is to realize is that r is still a constant, so we just have to remember that r is a constant. So, okay, all right. Okay, so what do we do now? Well, you can see here this just simplifies to dt. This we can take the 1 on k out, and then we get this integral here, which is a log. Okay, 1 on q minus r dq. Okay, so we now basically end up with what? Therefore, t is equal to 1 on k, 1 over k. Okay, now that becomes an ln, a log, then log to the base e of q minus r, and then we have this constant of integration c on the end here. Then we multiply everything by k, and we get a kt equals k ln q minus r plus kc. Put the kc on the other side, and we end up getting what? Kt minus kc is equal to ln q minus r. Then we raise everything to the power e. Then we get something like e to the kt minus kc is equal to what's that? E to the, now this becomes e to the ln of q minus r, and as you know these are inverse functions, so that will just drop out at q minus r. Okay, so this becomes what? E to the kt minus kc. Now I'll just let t equal 0, and let's say, 0, that's q. Actually, let t equal 0. Oops. Okay, hold on, we just wiped out a bit too much there. Okay, so if we let t equal 0, okay, what happens? Well, you can see here that e to the kt minus kc, okay, therefore we have what? E to the power of kt, which will be 0, minus kc becomes a kc, is equal to just q minus r. And we can let this be some other number, obviously. Initially, usually it's some sort of, let's let it equal a, for instance. Okay. All right. So we now have that e to the minus kc is some value a, another constant, okay, which is the difference between initially Q's, normally is applied to temperature, Q's original temperature, for instance, minus the room temperature. If you like, think of R as a room temperature. I'll just rewrite this over here, and you can see here we have now, therefore, what? Q minus R is equal to now e to the kt times e to the minus kc, and as you note, we just actually let that equal a, so I'll just replace that with an a, so that becomes an a, and actually I'll put it at the front. So we'll just rewrite that as a e to the kt, okay, and then we put the r on the other side, okay, therefore q is equal to r plus a e to the kt. Now, we just have a quick look at the graph. Now, what is this? So we have say an axis here, we have a time axis here and a q axis here. You can see here that there is some sort of value here at r. Okay, we have this is r, and you can see here, if as long as k is negative, which it usually is in this case, if k is negative, the limit of as t approaches infinity of q is actually r. Now it's coming down from above, so it's adding on. So it's actually coming down like this. Okay, so you can see here this is well, Newton's law of cooling is a typical example of this, which we'll have a look at shortly. Well, okay, here we have a problem about it's actually the coffee cooling problem, where the coffee is actually cooling from 80 degrees Celsius to about 75 degrees Celsius. You can see here about 1.5 minutes. Okay, and assuming you can actually drink it at 60, how long before you can safely drink the coffee? Okay, so we basically need to solve this differential equation. Okay, so let's actually start. Okay, so we know that dc, okay, dt, as you can see here, is k c minus, normally the actual 20 is actually the room temperature and these sorts of things, but okay, so let's actually turn it upside down. So dt, okay, dc is equal to 1 over, let's just find the reciprocals of both sides, c minus 20. Okay, we integrate actually with respect to c. So I'm going to shortcut a few things here. So we're going to just jump down to integral of dt dc with respect to c will be just integral dt. This would be, okay, the integral of this with respect to c would be 1 on k. I'll just write the integral of d, okay. This is going to be dc over c minus 20, which is going to be an ln. So we are going to get what down here, that t would be equal to 1 on k ln c minus 20 plus another constant. I'll call this other constant, we've got k's and c's floating around here, so let's just call this other constant, I'll just call it c1 to differentiate it a little bit from the other constants. Okay, so now, therefore, okay, we have what kt is equal to ln of, now c, this is the coffee's temperature, minus 20, okay, plus a kc subscript 1, okay. Then we just put the k subscript, c subscript 1 on the other side, so we get what, kt minus kc1, okay. This is the constant of integration, equals ln c minus 20, and then we raise everything to the power e, and we end up getting e to the kt minus kc1 is equal to e to the ln c minus 20, and as hopefully we remember, these are inverse functions, and this will just equal c minus 20 over here, and this is just e to the kt minus kc1. Now, what we normally do now is we say, look, just assume t is equal to 0. Okay, let's assume t is equal to 0. So, therefore, when t is equal to 0, let's have a quick look what happens. T is equal to 0. Okay, the serving temperature was 80, so we know that C is actually 80, so therefore, if you like, 80 minus 20, okay, obviously, which is just, as you can see, is just 60, okay, is equal to, obviously, 60, and that's equal to, now, T is equal to 0, so it's e to the minus kc1. So that constant, e to the minus kc1, is actually written as 60, and we need to rewrite this. Okay, so let's just rewrite, okay, the solution. So let's, hold on. So we'll just rub out some of this. Now, we need some of this, so I'll just rub out a bit of this. Okay, so we've now, what have we got? We've got that e to the minus kc is, you can see here, 60. So what have we got? Well, we had, what? C minus 20 was equal to, you might remember, e to the kt minus kc1. And that turns out to be, okay, obviously just e to the kt times e to the minus kc1. And we know that that's actually 60, so we write that as 60 lots of e to the kt. And that's c minus 20. And we put the 20 on the other side, okay. Therefore, the coffee's temperature at any particular time is actually 20 degrees plus this cooling exponential here. Now, okay, so the first thing is now obviously to try and work out what K is, the actual, I guess you could say the decay constant, I suppose you could say. Okay, so let's actually try and work out what K is. Okay, so how are we going to do that? Well, the first thing is we know that when T is equal to 1.5 in terms of minutes, okay, the temperature of the coffee actually has dropped down to 75 degrees C. Okay, therefore we can say, okay, what? 75 is okay, equal to 20 plus 60 lots of, now it's going to be E, now it's going to be 1.5 times the K, okay, because the T is 1.5. Okay, so we then have to rearrange this. We end up take off 20 off both sides, and we get what? 55 divided by 60, so we get 55 over 60, which we just see is 11 over 12. Okay, and that's equal to, okay, I'll just, okay, here is equal to what? E to the 1.5k. Now we're going to have to take the logs of both sides, as you can see here. So we're going to need to take the logs of both sides to bring that 1.5k down. And we'll probably just, okay, so let's just do that. And I'll just rub out some of this over here. Okay, so what's going to happen now is what? Well, the ln of 11 on 12, okay, if we take the logs of both sides here, is actually equal to the, okay, the ln of e to the, you know, to 1.5k, and that gives us just what? 1.5k ln e of e, which is, as you know, 1. Then we divide by 1.5. Actually, let's actually just rewrite that in 1.5 is 3 on 2 k. Okay, what is k? Well, okay, therefore, what k is actually 2/3 of ln 11 on 12. Now, if you work that out, you'll end up that's actually going to be a negative value. So the actual coffee's temperature obviously is decaying, if you like, or cooling. So we're now going to need, okay, so this value here, let's have a look. So this is the k value, right? That's the k value there. We're going to put it in up here, the k value up here. So this is then going to give us a coffee temperature at any particular time with that particular decaying constant, if you like. Okay, so let's actually do that. Okay, so let's actually, so we now know that really the temperature, the coffee's temperature, C, is going to follow this particular function, plus, if you like, 60. Now it's going to be E. Now we know that K is, what, 2 on 3, ln 11 on 12. And what we're actually after, there's a T, which I'm going to write in red in a second, but this T, the time, this is the time we're after, okay. So basically we need to solve this, okay, so this is the T we're after here, and we do know the temperature over here, well, the coffee's temperature would in fact be 60 if we're assuming it's safe to drink at 60. So we need to basically solve what? Well, we need to solve 60 is going to equal 20 plus 60 lots of e to the 2 on 3 ln 11 on 12 t. So we're going to basically now need to solve this equation for this t here. Okay, so first up, how are we going to do that? Well, you can see that we just take the 20 off the 60 to start with. Okay, so let's do that. Okay, so let's do that now. Okay, so we end up getting what, 40? Therefore, 40 would equal 60. Okay, e to the 2/3 ln, okay, 11 on 12, and there'll be a t. a red t here, which is what we're after. Okay, so we can divide by 60 and get 2/3. So let's actually just do that. So we end up getting 2/3 equals, okay, e to the 2/3 ln 11 on 12t. Now, okay, we need to get this down to get the value of t. So we need to take the logs again of both sides. So let's take the logs of both sides. Okay, so ln 2/3 equals, okay, we take the logs again, and this power comes down, and we get ln of. Welcome to Maths with Bob. Today we're looking at applications of calculus to the physical world. This is the second in the growth and decay series. Okay, now today we'll actually have a look at well, something like Newton's law of cooling, where the rate of change of the quantity with respect to time is actually proportional to not only the quantity, but it's actually the difference in some sort of constant called r. This one here is actually a constant. A lot of times it's the room temperature, but it doesn't have to be. Well, okay, what does t equal? Well, you can see here we need to make t the subject, and we can see here that what t will be equal to ln of 2/3, all divided by 2/3 of ln of 11 on 12. Now, when you actually do this on the calculator, you get time is about, well, it's a 6.9898. So it's approximately, say, 7 minutes, which does seem a fairly long amount of time to wait to drink your coffee. But that's all for today. Thank you for watching. Bye for now.